Good morning, friends! We are from Isaac Newton's group, and we are going to explain to you about double integral, triple integral, and its application. My name is William Christopher.
My name is Rifda Anindya Putri.
My name is Haekal.
My name is Henokh.
Okay, so the first topic will be explained by my friend Haekal.
Let's go to the class.
So the first one, our group will explain about double integral on over rectangular region. The first one is this: we have two integrals. The inner one is x. We need to evaluate x and treating y as a constant. Then we evaluate the outer integral. This is where we got the interval. So y equal to 1 and y equal to 2. X equal to 1, x equal to 3. This is the image where this plane over xy plane. By using Fubini's theorem, we know that to convert an iterated integral into the constant. So the first one, we need to take the inner integral, then evaluate it. We got this result. Then put 3 and 1 into x, where we treating y as constant. This is the result. The last one, we evaluate y integral, then we got this result. Finish.
So thank you for listening, and the next topic will be explained by my friend.
Okay, so I'm going to explain to you about the double integral in polar coordinates. So let's go to the class.
Yeah.
Hello everyone, back with me again, William. Of course, you all know about the basic of double integral. Now, we will be moving on through double integral in polar coordinates. But before that, you should all know about three basic equations of polar coordinate. The first one is x equals r cos theta. The second one is y equals r sin theta. And the third one is x squared plus y squared equals r squared. Why you should all remember these equations? Because it will come in handy when we are discussing about the problems of the double integral in polar coordinates. Okay, so this is the fundamental equation of double integral. Then we can represent this equation into the polar coordinate system. So we can substitute the limit d with alpha to beta in respect to theta. Then we can substitute also h1 theta to h2 theta in respect to r. Then we can substitute fxy with fr cos theta, r sin theta. Then we can substitute dA with r dr d theta. Okay, so the next video will be about me explaining to you about the problems of double integral in polar coordinates. Thank you. Okay everyone, so we got this problem, which is an example of a problem of double integral in polar coordinates. So fr theta equals r squared, which is limited by with respect to theta by 0 to 2y, and with respect to r from 0 to 2. So we have this problem to solve. Notice that this is a little bit different from the previous equation, but fear not, because it remains the same. Why? Because if we switch these boundaries over here, the integration boundaries, and we also switch the sign over here, it will remain the same. So we are doing some calculation. So first, we can factor out the r cube from this integration, from the blue one, into this, because it is a variable of r. Then we can integrate this integration to become like this. It means that the integral from 0 to 2 of r cubed times 2 pi dr. Then we can factor out the 2 pi out of this integration, because it doesn't have the variable r. So like this, where we can calculate the integral of 0 to 2 r cubed dr. Okay, so the result is this. 2 pi times r to the power of 4 divided by 4 of 2 to 0. So we can substitute r with 2 and we can substitute r with 0. We come up with the result like this. 2 pi times 2 to the power of 4 divided by 4 minus 0 divided by 4. Okay, so we can come, the overall result is 8 pi. So which is the result and also the answer to this problem. Thank you everyone for listening.
Okay, friends, we have explained about the polar coordinates in double integral. Now, the next chapter will be discussed by my friend.
Okay, for the third chapter, I will explain about double integral in surface area with the cameraman. Let's go! And now I'm going to tell you how to find the surface area through double integral. So this is the question. Find the surface area of z equals to x times y inside x squared plus y squared equals to 1. This is a diagram from the question above. And this is the basic formula to find the surface area. The first thing we need to do, we need to find the derivative of dz divided by dx and dz divided by dy. We consider this as the coefficient when we derivative it. So when we derivative it, it becomes y and this one becomes x. When we input to the formula, it becomes 1 y squared plus x dy dx. This is the Cartesian form. So we need to change it to the polar coordinate form. From the formula, this is the formula of polar form, and we need to change this equation to this. So it becomes 1 plus r squared, and we need to change the dy and dx into r dr d theta. So we need the second step. We need to find the boundaries of this equation. The boundaries is we need to find the minimum and the maximum value of r. So the minimum value of r is 0 and the maximum value of r is 1. So this is 1, this is 0. And the second boundaries we need to find it from the theta, because it's a circle. Circle is 360 degrees, which is 2 pi, the maximum value, and the minimum value is 0. So this is the equation. And then the next step, we need to change this into u form. So it becomes equals to u. So we derivative it becomes du to r dr. So dr equals to du divided by 2r. So we change this to this. So it becomes of u du to r d theta 1 0 to 1 0. And then we can cross it, so it becomes 0 u half du d theta to 1 0. And then we integral it, it becomes this is the boundaries 0. When we input the value of 1 and 0 to the equation, we can cross it. It becomes 8 minus 3 d theta. This is still the first boundaries, so we need to find the value of the second boundaries. So I can just simply put it in here, 2 pi 0 8 d theta. Okay, so we integral it simply. It becomes theta minus 1/3 theta with the boundaries of 2 pi and 0. When we input the value, it becomes 2 pi minus 2 pi 1/3. we can simplify this equation into plus 3. So this is this one. So this is the surface area from the question above. Thank you for watching, and I hope you can learn well. Okay, now I've explained it, and I hope you guys can enjoy my explanation. Now the next chapter will be explained by my friends.
Okay, the next chapter will be explained by me. The next chapter will be triple integral. Let's go. In this section, I want to tell you about triple integrals done completely in cylindrical coordinates. Recall that cylindrical coordinates are an extension of polar coordinates into 3 dimensions. The following are the conversion formulas for cylindrical coordinates. In order to do the integral in cylindrical coordinates, we will need to know what dv will become in terms of cylindrical coordinates. We will be able to show in the change of variables section of this chapter this dv equals r, dz, dr, and d theta. This is the formula of triple integral in cylindrical coordinates. I will give you an example how to evaluate triple integral in cylindrical coordinates. Evaluate triple integral of y dv, where E is the region that lies below the plane z equals x plus 2 above the xy plane and between the cylinders x squared plus y squared equals 1 and x squared plus y squared equals 4. First, you have to find the range for z, and then you have to find the range for region D, and then you will have to evaluate the triple integrals, and then you will find the result is 0. Yay! In the previous section, we looked at doing integrals in terms of cylindrical coordinates, and we now need to take a quick look at doing integrals in terms of spherical coordinates. First, we need to recall just how spherical coordinates are defined. The following are the sketch shows that the relationship between the Cartesian and spherical coordinate system. Here are the conversion formulas for spherical coordinates. And we also have restrictions on the coordinates such as to use triple integral in spherical coordinates, you have to change the dv into this formula. And then the formula for triple integrals in spherical coordinates is this one. Next, I will show you the example for this topic. Evaluate triple integral of 16z dv, where E is the upper half of the sphere. X square plus y square plus z square equals 1. We are taking the upper half of the sphere. The limits for the variables are this 3. And then the integral is this. You have to evaluate the integral, and then the result is 4v.
So friends, we have discussed and explained to you about everything to know about double integral and also triple integral. I hope that you guys understand, and
If you have more questions, you can ask Mr. Askar. Don't forget to subscribe and give it a thumbs up.
Thank you for watching.
Yeah.
Kocak deh.